Good morning, everyone. I'm Sichun Liu from Xidian University, and today I'm going to talk about how to conduct the on-demand deep model compression for mobile devices through a usage-driven model selection framework. This work is joint with Rice University and ETH Zurich. As we know, machine learning and cloud computing has stimulated a lot of intelligent applications on a wider range of mobile and IoT devices, such as the Face ID, Siri, and the Amazon Echo. However, they cannot work under a poor network condition. Also, today's most accurate and robust recognition are built on the deep learning. So there is a growing trend to bring the deep neural networks powered intelligence to the mobile and IoT local devices. However, the successful deep neural networks are always compute intensive and storage exhaustive. It cannot fit into the resource constrained mobile devices. To trim down the deep neural network complexity, the compression technique is a commonly used method. However, most of the prior deep neural network compression techniques always provide a one-fit-all solution without considering the diversity of the platform and the application. Also, the multiple techniques are always manually selected. So in practice, we have a lot of data and models for different applications, and they will be deployed on diverse diverse platforms. So it raises a challenge for the developer how to automatically generate the most suitable deep neural network to meet the different application requirements and the resource constraints. To solve this challenge, we present the AddDeep. It is an adaptive and automatic deep neural network generation framework. The non-expert developer only need to input their user-specified baggages, and the device imports the constraints to the AddDeep framework. The AddDeep can first select the initial deep neural network based on the input data size, and then we can calculate and quantify the user demand. Finally, we can use an optimizer to solve the user demand problem and output most suitable compressed deep neural network to meet the developers' requirements. And here we have two challenges. The first one is how to derive the latency and energy cost because these two resource performance depends on the platform, and we need to derive them during the model training phase. And the second challenge is there are a lot of compression techniques, and the combination of multiple compression techniques, the search space is very huge. How to have a closed form solution in this huge search space is a challenge. The first challenge as shown in this picture, we can see that we need to maximize the accuracy, minimize the energy cost, and constrain them into a latency and storage bucket. But the energy cost and the latency depends on the different platform, and it can be tuned by applying different compression techniques. So here we need to build the estimation model to give the energy cost and the latency during the training phase. The second challenge is there are a lot of compression techniques. They can apply to the different layers of a deep neural network model. So when we combine them, the search space is very huge. To solve the second challenge, we use the deep reinforced learning method, the DQN, for the deep neural network compression. Here we select the DQN not only because it can conduct the automatic decision, it is suitable for the non-differential optimizer. It is flexible to add or delete more selections. But also, the DQN is essentially a deep neural network, so the original DNN and the DQN controller can be end-to-end trained. Here, in order to reduce the search space, also speed up the DQN training, we use the feature size rather than the feature as the input to the DQN. And within the DQN part, we separate, in order to always guarantee the constraint, we separate the objective gain and the constraint satisfaction into two model streams. And a very important step in the DQN is to define the reward function. Here we need to define the reward function based on our user demand. So we separate the objective gain and the constraint satisfaction into two streams to always guarantee the constraint. In order to evaluate additive, we test the additive on 5 data sets with 3 initial deep neural network models over 6 smartphones, 2 watches, 2 device boards, and 2 smart gateways. And we select 10 baseline compression techniques which can be applied for different layers of the model. And we first compare the performance of one compression technique. We can see that no single compression technique can achieve the best overall performance. Next, we compare the performance when combining 2 compression techniques. We can see that some combinations of 2 techniques can dramatically reduce the resource cost than using single technique, but others may lead to a performance degradation. And also the searching space of combining 2 compression is huge, so we need an automatic selection framework. To show the performance of our proposed DRL optimizer, we compress the DRL with other optimization schemes, the gradient and the exhaustive one. We can see that the DRL outperforms the other 2 schemes since the runtime performance is adaptively feedback to the DRL decision. And then we test additive over different tasks. We can see that no one fits our compression technique for all tasks. And we also test the additive on 12 platforms. We can see that the additive adaptively selects the best compression strategy for diverse resources. And also we found some new combination. This is not found by the prior works. This is the first work to integrate the deep model compression into an automate hyperparameter tuning framework, and also we present a new optimizer to automate the compression technique combination. And we conduct exhaustive evaluation on 10 baselines over 5 tasks and with 12 platforms. In our fieldwork, we will expand the additive to the standard hyperparameter tuning. Thanks.
Okay. Thank you, speaker.